Welcome back. Now we will begin the practical journey creating our own dataset. We generate the x values from 0 to 2 by using NumPy's line space that gives us evenly spaced point across the sine wave. For each x value, we will compute y is equal to sine of x to get the true values. You can also add a little noise to simulate the real world signals for sensors have always noises. Then we'll normalize the values. The normalization helps in stability. And finally visualizing everything in a matplotlib for immediate confirmation. This is the code. You can actually use this code as your reference and write your code in a Google Colab. And this is the generated noisy sine dataset. Earlier you would have seen a pure sine dataset without any noise. Here this is a noisy sine dataset. Machine learning needs a proper evaluation. That's why we split the data into training, validation and test sets so that the model generalizes well. This is a common practice in machine learning to prevent overfitting. So what is a training set? The training set teaches the model to learn patterns. Validation set. It helps tune the model during training. Finally, test set. Final benchmark for evaluating generalization. So we use tools like train, test, split in skit learning or slicing in NumPy to make this easy. It's important that all split represents the same distribution so the model doesn't get biased. So imagine learning math from textbooks, practicing with sample questions, then writing it for your final exam test. So similar we are using here. So training our model, validating and testing. Here I am actually training a data set. Previously I have generated 1000 data sets. Here I am going to train 60% on training and 20% in validation and another 30% for test. You can actually make it so that you can own calculations can happen. So our network here will use ReLU activation function. ReLU stands for rectified linear unit. This is one of the most commonly used activation functions in deep learning. The mathematical formula is f of x is equal to max 0 of x, 0 comma x. So if the x is positive, we will keep it. If it goes to negative, we set it as 0. Simple, right? So why we use it? It makes networks non-linear. So neural networks can only learn complex pattern if we introduce non-linear transformation. ReLU is simple yet powerful non-linearity. Sine is actually non-linear, so we are using this one. Next is simplicity. ReLU is easy to compute. No complex math like exponential or tan. Speed. Models can train faster with ReLU compared to sigmod or tan h because it doesn't saturate in the positive neurons. Avoid vanishing gradients. Unlike sigmod or tan h, gradients don't vanish. When values are large and positive, helps deeper networks learn efficiently. Think it as a diode in electronic. It passes current in a one way and blocking the negative part. With this we can define the network itself in Keras. Now that we have prepared the dataset, we can actually define our neural network using Keras, high-level API inside a TensorFlow. We'll use the sequential API which lets us build the model layers by layer in a straight line. That's what the Keras is. So our Hello World model has 3 layers. First layer is input layer which takes single input ex. And second is a hidden layer with 16 neurons. Using ReLU activation, this is where model learns this non-linear singular pattern. Final is output layer. So output layer has only one neuron which predicts a sine wave. So we compile the model with mean squared error MSE as a lossless function and RM is prop as the optimizer. We call model.summary. We can see that this network is extremely lightweight, ideal for running in a microcontroller because it only has 16 hidden layers. So think it as a sequential as stacking Lego blocks like input, hidden and output. Each fits neatly into this. So once the architecture is ready, the next step is to train with multiple epochs and batches. Training doesn't happen in a single pass. Epoch is one full pass through the dataset. So we'll use multiple epochs. We process the data in smaller groups called batches to make the training more efficient and stable. Smaller the batch, faster but noisier updates. Larger batches, smooth but slow training. So we don't feed all the data and so on. We'll just use in single batches after batch. So the weights are updated. We'll use in this project we are using a batch size 16 and first initially we are taking at a 500 epochs, 500 training sets, then we'll do it 1000 once so that you can clearly see the difference for the overtraining the data. So this allows a small network to gradually refine its predictions and helps learn sine wave pattern smoothly and gradually. Think of epoch as studying a book multiple times. A batch size is how many pages you are going to read before taking a practice quiz. Now let's run this training process in Keras using the model.fit function. During training, the model performs 3 steps, or it learns patterns from data. For that, first it predicts the output of the given x. Second is compares with the true sine value using lossless function. Next, updates the weight using optimizer. So here you can see the training values for the error in training loss and validation loss. We use MSE as loss since it punishes larger errors more strongly. Over time, minimizing the MSE leads to smoother prediction. As he can see after the MS is updated, the training and the validation for 1000 data is nearly equal. We also check the validation loss on unseen data to prevent overfitting. Keras handles this entire loop automatically once we call the model.fit, the function. Let's see it in the next slide. So training with the model.fit. The core command that makes training simple. This is the training. The Keras takes care of forward passes, calculating losses, back propagation, weight updates. It also records training progress into a registry object. You can also later plot lossless curve, which we see in the previous slide. You can also add callbacks like early stopping, which halts the training if validation loss stops improving. Think it as a model.fit function as an autopilot of training. You tell how many times to study. Like the batch size here, I said 500, and the graphic could have said 1000. And you can tell how many times to study the epoch, and it runs everything automatically. It automatically uses gradient descendant and tracks loss and optional validation loss. Helps visualize using matplotlib for your. And how do we measure the success? That's where the training metrics come in. So understanding the metrics. Metrics evaluate how well the model is learning and generalizing. Like I said earlier, MAE actually punishes the model. So it helps us identify overfitting or whether the training is moving in the right direction. So metrics is like a progress report for the model. The main ones here are training losses, error on the training data, validation losses, error on unseen data, MAE, so mean absolute error which we are using, average error in original units. So this is a question. And also a good model has low training and validation loss. So it like both decreases steadily. And example, if a true value is 0.7 and predicted is 0.5, the error is just 0.2. MAE tells us average size and such mistakes. So other common metrics here, RMSE, root mean square, error originates in the target, or R2 score, how well the prediction matches the variance of the actual values. So low training loss but high validation loss, it's actually overfitting. Based on the graph you can actually calculate if the model is overfitting or not. So graphing or plotting this training history. Plotting loss is epoch shown whether the model is improving. So if the curve goes down and levels of the model has learned, if the training loss drops but the validation rises, it's actually a overfitting. So for our sine wave model, we expect smooth decreasing curves with training and validation loss close together. Visual feedback is crucial. Without it, we cannot judge if the model is underfitting, overfitting, or just right. So check if the model is converging. You can see how well the model has learned to mimic the sine wave. So in next slide we'll revisit the lossless function and optimizer that whole process. So the lossless function tells us how far off the predictions are. For regression we use MSE, mean squared error. The optimizer detects how to adjust the weights to minimize the loss. Here we are using RMS prop, which adapts learning rates dynamically and works well with small and smooth problems. So lossless function analyzes larger prediction errors, and RMS prop, root mean square, adaptive ideal for smaller models. So together they ensure the model steadily learns this kind of. The choice affects how quickly and accurately the model learns. So we use MAE, absolute mean error, for easier interpretation. So loss is like your distance to the target, and optimizer is your GPS telling you how to steer. So we plot this training data to see how well the model is learning. Good model shows decreasing and training over the epochs. So we use matplotlib to plot the losses as epochs, and healthy curve shows a sharp drop at the start after 300 to 400 epochs. We can see there's a drop, and the loss is high and flat. The model is underfitting. And if the training and validation diverge, it's overfitting. So here we can actually see the model is actually overfitting. We don't need 1000 data. It's more than enough. We use just 500 to 600 data. So this visualizer helps decide whether to stop training, increase epochs, or modify the model. So what if the model isn't good enough? So we have to improve the architecture from the starting. This is the first gateway for which we can go through this CAA process. Up until now we have trained our model on the training data and checked its performance using validation data, but there is still one more crucial step: testing. So earlier we have set aside 20% of the data set exclusively for testing. This data was never used during training or validation. Why? Because we tune our model based on the validation performance. There is always risk that we accidentally overfitting to the validation set. By testing on the completely fresh, untouched data, we can be confident that the model generalizes well to the new inputs. So it's very important that once we use the test data, we don't have to tweak the model any further. If we did, the test would effectively become another validation set. We'll lose our only measure of true generalization. The model performs badly on the test data. It's time to go back to the drawing board, adjust the architecture, and try again. So this prevents false confidence from overfitting on the validation data. This is the comparison, or the actual versus the predicted sine wave. So testing is like a final exam. Validation is like a practice test. If you keep practicing on the final exam, you'll never know. You'll really learn the material actually. Finally, improving the model. If the prediction sine wave looks too linear, it means the model doesn't have enough capacity. So we can fix it by adding more neurons or hidden layers, training longer, like adding more epochs. In fact, moving to 2 hidden layers with ReLU activation gives model more power to capture sine complexity. Model building is iterative. Define, train, evaluate, and improve. That's it. So once the model is accurate enough, the next step is preparing it for deployment. We have seen now how to define, train a neural network in Keras, starting with a simple architecture. Input, hidden layer with ReLU, and output. We trained the approximate to the sine wave. Along the way, explored the meaning of epochs, batch size, and also metrics like loss, MAE, visualize how the training process looks over time. We also learned how to detect the issues like underfitting, overfitting by the looks of the curves, and also how to improve the model by adding more neurons, or by training longer, like adding more epochs, more data. This section has given you a foundation for the model training in TinyML, building a data set, defining a network, training and refining it or improving it. So in next session we will see how the trained model and make it ready for deployment. We will convert it into the TensorFlow Lite, transform it to C array, and finally embed it into the Arduino firmware so we can run it in the real hardware. Thank you.